let me introduce here the Cantor set. This is a very important set that is used in analysis when you want to provide examples and counterexamples. And it has many counterintuitive properties. We will see some of them. But how is the Cantor set constructed? The one we are going to see here is what is called a ternary Cantor set. And it's called ternary because it's constructed iteratively from 0, 1. Okay, so we will start with the segment 0, 1, the closed interval, and we will mark the 1/3 point and 2/3 point. This is why it's called ternary. And once we do that, those points we will need to keep for reference. The next step of the construction is to remove the middle third of the interval. So in the second iteration, which is called E1, we are going to keep 0, 1/3 union with 2/3 1. So that is our E1. Now, the next step for E2, what I'm going to do is again remove the middle thirds of my set and then keep track of those points. Let me use a dashed line. Okay. And I will just keep doing this over and over. So now, of course, I need to, all the segments that I remove, they are already out for good. Okay. And now again, I remove the middle segments. And I keep doing this. This would be my my E3. And I keep doing this over and over and over. Okay, these are just a few generations. And eventually the set becomes very sparse. Okay, so let's write what would be E2. E2 would be 0, 1/9 union with 2 9s, 3 9s, union 6/9, 7/9, union 8/9, 1, and so on. Okay, if we continue in this way, we find a sequence of sets En that has two properties. The first property is that it's a nested sequence. You can see from the construction that its set is always contained in the previous one. And then the second is that each of the En is a union of 2 to the n intervals of length 3 to the negative n. Okay. So then we define the intersection of all these En from 1 to infinity is what is called the ternary Cantor set. Okay. Now, here, notice one thing. The En are all compact and they are all non-empty. So we have, by the Cantor's intersection theorem. Let me write by Cantor's. There we go. We have that P is non-empty. Okay, so we actually, because you might argue like we are taking so many points out from this, are we leaving any point behind? The answer is yes. Okay, it turns out this is the P is a compact set and it's non-empty. So let's discuss some properties of the Cantor set. Properties. The first property that I have just mentioned is that P is compact. Okay, the second one is that P is a perfect set. Well, let's leave it P is perfect. For this, you need to show that P has no isolated points. Okay, the details are in the book. The third property is that P is uncountable. Which is very interesting, if you notice, because we started with the interval 0, 1, remember? So we started with 0, 1, which is uncountable itself. And we started removing large chunks of the interval at each step. And it looks like in the limit, we are going to be left with almost nothing. But what we are saying here is that P is uncountable. And why is uncountable? Because it's perfect, and perfect sets are uncountable. We have seen this theorem in a previous video. Okay, so here we are. This is definitely very counterintuitive because it looks like we are taking an uncountable set 0, 1. We are removing most of it, and what is left that looks like nothing is uncountable itself. So that means that in some way we have left most of the set. But then P has length 0, which is a different way. That means that in a different way, we have actually removed most of the set. Okay, we can show that the length of 0, 1, the complement 0, 1 minus P is 1. So that means that if we take the lengths of all the pieces that we have removed and we add them together, what we are going to get is as long as the interval 0, 1. And finally, I would like to mention that the Cantor set is an example of fractal. Fractals are self-similar. Well, P is self-similar. So that makes it a fractal. You may have heard of fractal sets. Fractal sets have very not very intuitive properties. Okay, one of the properties of fractal sets is that they don't have a dimension like the way we are used to. In the case of the Cantor set, the dimension of P is neither 0, neither 1. It would be 1 if we thought about it as a solid segment, right? The line has dimension 1. We could think the dimension should be 0 if we just look at the points, because it's a bunch of points. The thing is, it's a bunch of points with a very particular structure that makes it gain some solidity in some way. It's like a foam, if you want. And it has a dimension that is not an integer number. It's a number between 0 and 1. Okay, and actually that property was very useful to me in a research article. That's way beyond the scope of the course, but what I'm trying to say here is that counterintuitive as it is, it's useful. Okay, so this is probably one of the first examples of a fractal set that we are going to find.